This is Project 1.4, the 2-bit adder. This project focuses on binary addition. Binary addition is a part of binary arithmetic. Computers, phones, and tablets, and many other electronic devices use binary addition as they include digital circuits. Binary addition is used to store and process data in electronic devices. The purpose of this project is to gain understanding of binary addition using 3 prototypes plus a final prototype. The way binary addition works is it starts from the right, the least significant bit, and goes to the left. If both of the rows to the right add up to 2 or any other decimal positional numeral system type of number, they have to be carried over to the next column. This project consists of a half, full, and 2 2-bit adders, one of them being a PCB. And all these prototypes other than the PCB are made on a breadboard to demonstrate binary addition. Let's start with the half adder. As seen, the half adder is made up of 2 momentary push buttons, A0 and B0, 1 green LED, 1 red LED, 2 1K ohm fixed resistors, 2 470 ohm fixed resistors, 1 MC14070B logic chip, and a CD4081 logic chip. All of these components are necessary for the addition of binary numbers up to 2 using binary. The parts table shows the components. First, when none of the buttons are pressed, no LED will turn on, displaying off, which is represented by 0 in the truth table. When the first switch, A0, is pressed, the red LED turns on. This is because 1 plus 0 is equal to 1. Red represents 1 in this case. When the second button is pressed, the red LED will turn on again because 1 plus 0 keeps equating to 1. This is because of the same equation, and the final possibility of the half adder is when both of the switches are pressed, and this results in the green LED turning on. The reason for turning on of the green LED is because 1 plus 1 equals 2, but we are using the binary number system and not the decimal positional numeral system. Moving on to the next prototype, the full adder. The full adder consists of 3 momentary push buttons, 2 LEDs, 1 red, 1 green, 5 1K ohm fixed resistors, an MC1470B logic chip, a CD4081BE logic chip, and a CD4071BE logic chip. As seen, the full adder requires 2 half adders made up of XOR and AND gates, and also has an additional OR gate, which is a 4071 logic chip. The purpose of the full adder is to have the ability to add 3 binary bits A0, B0, and the C input, which is the carry. The circuit diagram on the right shows that the high inputs from A and B into the XOR gate output a low signal, and the AND gate, however, outputs a high signal as a result of 2 high inputs. Then the high output becomes an input for the OR gate, and the second input of the OR gate, which is low, outputs a high into the green LED, which is the carry. A and B are added to output 2, but it has to move over 1 column because only 0s and 1s are used in binary. Here's a visual of the turning on of the green LED and the off state of the red LED. The truth table shows the 8 outcomes of the inputs. The full adder requires 3 inputs, A, B, and the C in or carry input, and 2 outputs, sum and carry, represented by red and green LEDs. The procedure presented above shows the state when both A and B are on and C in, which is the carry input, is off. This is displayed in the 7th row of the full adder truth table. This proves that it outputs a high into the green LED because it is the carry, and it carries over the extra 1 to the next column. Next prototype is a 2-bit adder. The 2-bit adder prototype is made up of 4 SPDT single pole double throw slide switches, a 4070 logic chip, a 4081 logic chip, and a 4071 logic chip. It includes 2 red LEDs and a green LED representing carry. It also includes 3 1K ohm fixed resistors, a 9-volt battery source, and a 1N4001 power diode to keep current flowing in the same direction. The 2-bit adder circuit diagram shows that circuit is made up of 3 half adders and an OR gate. The truth table of the 2-bit adder, where A0, B0, and A1 are on, shows the reason why the XOR does not turn on. This is because there are 2 high inputs. Looking at the truth table of the XOR shows that 2 high inputs output a low for the XOR. The AND gate gets 2 high inputs, which outputs a high into the third AND gate. The third AND gate also gets its second input from the XOR gate, which outputs a high as well. This becomes one of the inputs for the OR gate, and the high and the low input of the OR gate, as a result of the last switch not turning on, output a carry. When 2 switches, A0 and B0, are on, According to the decimal positional numeral system, it would be 2, but binary is necessary here, so it results in being carried over to the next column and being added with the other one, and 1 plus 0 results a 1 and a 0, and in the decimal positional numeral system, this would be the number 2. The final prototype is a 2-bit adder PCB. It is made up of a total of 4 rocker switches, 3 logic chips, 4070, 4081, and a 4071, 4 screws, an RSGC Aces Casano case, and a terminal block and a shooter power jack. This works the same way as the 2-bit adder circuit we've had previously, and similar components are used in this final prototype. I hope this video is helpful in your understanding of binary addition using half, full, and 2-bit adders. Thanks for watching.